Hi, everyone. Thanks for having me. This is my first time being here at Disobey and Helsinki, and I love it so far. So my name is Zoltan Balazs, and today I'm going to talk about how to hide your browser zero-day. But first, just a quick introduction about me. I do a lot of offensive research. For example, some years ago, I wrote a tool called Zombie Browser Toolkit, which has some malicious browser extensions in it, which you can use in Chrome, Firefox, IE, or Safari to add some extra funky functionality to your browser. I also created the so-called hardware firewall bypass tool, which is basically a kernel driver in Windows, and you can use it to mess with hardware firewalls. I created a malware, which you can upload to some malware analysis sandboxes, and it will leak a lot of interesting and unique data from that malware analysis sandbox. So later on, you will know that if you see this data in an environment, then your code is running inside a malware analysis sandbox. I also did play a little bit with some crappy IoT devices, and I published some code which was a remote code execution code, and turned out it was integrated by the bad guys, and my code was running inside the Persirai botnet. So actually, I wrote a code which was running on 600,000 cameras. Yeah. And I also invented the idea of encrypted exploit delivery, which is going to be the topic of this talk. I'm the co-organizer of the so-called Hacker Shuli meetup in Budapest, and I'm in the program committee of the Hacktivity conference. So what I'm going to talk about today. First, I will give you a little bit of introduction of elliptic curve Diffie-Hellman and my encrypted exploit delivery project. I will talk about my attacker model. I will talk about why this is different or why this is new. And I will play a little bit of cat and mouse game with offense and defense. All right, so let's start with how did this story begin? Because I believe every research project has a story. So I had a discussion with some of these next generation or breach detection vendors. And I told them that I'm sure that there is a way how I can deliver my exploit to an endpoint so their network detection tool won't be able to see that there is an exploit here, and the network detection tool won't be able to see that there was also any malware delivered to the endpoint. They told me that's impossible. So whenever someone tells me something is impossible, this is what happens. So I went home and I started to code. But before going into the details, I want to ask you guys, why are you here and what might be interesting in my talk for you. So if you are an exploit broker or you are working for law enforcement, hands up. Okay, one guy, that's cool. Usually it's zero, but once I was at a conference when there was like 4 guys who were exploit brokers, but at different companies, so that was pretty nice. So for you guys, I can show you a way how you can prevent your offensive zero-day exploit code being leaked. If you are a pen tester or red teamer, hands up. Okay, a lot more. So for you guys, I'm going to show you a technique which you can use to bypass perimeter defenses if you are using exploits, and it might be able to also bypass some host-based IDS systems. If you are in blue team, forensic investigation, exploit kit researcher, hands up. Okay, so for you guys, I'm going to show you how your current defenses might be bypassed with my tool. and what you might be actually looking for if you are searching for advanced attackers. And for the rest of you, I think learning about elliptic curve cryptography is always fun. So let's start with the introductions. I'm going to talk about exploit kits and targeted attacks with 0 days. I will talk about the Diffie-Hellman key agreement, elliptic curve Diffie-Hellman key agreement, and encrypted browser exploit delivery, and how my idea was implemented by the bad guys at the end of the day. So an exploit kit is a software which exploits vulnerabilities. Okay, we know that. So what happens if you have a browser 0 day, for example, and you lose your browser 0 day? There was this story in 2016 that a journalist in the UAE was targeted by a special Safari browser 0 day. And luckily, the guy knew that he was targeted, and when he read this actual piece of text message, he knew that something fishy is going on. So he didn't click on the link, but he forwarded this message to some guys in Citizen Lab. And these guys went to a shop, bought a new iPhone, and they did set up a lab environment where they dumped all the network traffic. And when everything was set up, they just clicked on the link, analyzed the Wireshark dump. They were able to see that, yeah, there is a Safari 0 day in the Wireshark dump. They sent it to Apple. Apple patched the 0 day, and now the 0 day was lost. So someone was losing a lot of money due to this poor OPSEC. And there was this other attack where probably law enforcement was targeting some pedophile sites. And usually what they do is that they seize control of a web server, and they put additional scripts to the web server. So whenever someone visits the website, usually after login, they will deliver the exploit code to the visitors. And usually this exploit code is not a fully fledged malware. It's just an info leak code. In this case, it leaked the IP address, the original IP address of the visitor, so it was not hidden by Tor anymore. And it also leaked the machine name, and the MAC address of the machine. And what happened in this scenario was that someone quickly realized that there is an exploit code on this website. He posted it on a forum. Mozilla and the Tor browser guys quickly realized that there is a 0 day going on. So they reverse engineered the code, they patched it, and basically because of this happened so fast, the law enforcement guys, they were not able to catch so many bad guys. So in both cases, the exploits were burnt pretty quickly, and someone lost a lot of money. Now, let's talk a little bit about Diffie-Hellman key agreement. There is a very nice explanation on Wikipedia how Diffie-Hellman key agreement works with colors, and I really like this approach. So let's say that Alice and Bob, they want to communicate securely. So they want to agree on a shared common secret, on a shared secret they both know, but no one else knows. And meanwhile, they have public channels they can communicate with, and they have to come up with an idea how they can agree on the same shared secret. So let's say that they both start with a common color they both agree on. So let's say this is the yellow one. And now both of them, they choose their secret color, which no one knows except them. So Alice chooses some oranges and Bob chooses some, I don't know, it's green or something. Now, they can mix the common color and their secret color together, and they will get different colors for sure, and they will send this new color on the public channel to the other party. And in reality, of course, it is easy to subtract colors from each other. But for this example, just let's pretend that it is not that easy to do. For example, for me, from the top of my head, I cannot do that. So let's just say that if you see this brown color and this blue color, and you know that yellow is the common secret, you have no idea what the secret colors were. And now, if both Alice and Bob, they add their own secret color to this mix, they will see the same color, which is brown in this example. And this is a color which they can use as a common secret from now on, right? In math world, Diffie-Hellman key agreement uses modular arithmetic. So let's say that we use the number 13 in this case, and we multiply 2 with itself. And at the beginning, it's easy to see how 2 is moving around the clock. But after some multiplication, it just seems random. And this is a very basic and easy example. But in Diffie-Hellman key agreement, we are usually using very, very large numbers. And there is one very nice characteristic of this mathematical problem is that it is very easy to calculate it in one way, but it is very hard to calculate the other way. So if we are looking at this clock, it is very easy to find out how we get here. So if I choose a random number around the clock, you won't be able to know how I was able to get there. And you have to basically almost try all the combinations to see how I got there. And that's a nice property of this Diffie-Hellman key agreement. What's a bit different from the traditional Diffie-Hellman in the elliptic curve Diffie-Hellman key agreement, that it is much faster, which is very nice in my case. And when I started creating my proof of concept code with Diffie-Hellman, it turned out it is just too slow for JavaScript, and it's not feasible to do that with practical key lengths. I really don't want to go into the very deep details of how elliptic curve Diffie-Hellman works. Just think about like this is a billiard ball on the table, and if you know the starting position of the ball, and you know the force, and you know the vector, how you basically hit the ball, you can basically calculate where the ball will end up on the table from a mathematical perspective. But if I ask you that the ball was here and it get there, it's very hard to come up with a long path how you can get the ball from one point to the other point, right? So this is a very, very high-level overview of how elliptic curve Diffie-Hellman works. Now, this slide is pretty important. It's a bit complicated, but bear with me. I'm sure I will be able to explain it to you. So this is basically how my idea works and how it was implemented. On the left side, you can see the victim user who is browsing the internet with a vulnerable web browser. On the right side, you can see the attacker server delivering the exploit code and the malware. So as it is with every web communication, first the client has to start communication with the web server. So it sends an HTTP request to the server. Now the server will generate the elliptic curve Diffie-Hellman keys, and it will send the elliptic curve Diffie-Hellman parameters and the public key part of what he just generated, together with some crypto libraries, to the user victim browser. Now the browser will execute all this bunch of JavaScript code, and now it will generate its own secret Diffie-Hellman key. And because now it already has the public key from the server, it can generate the common secret in memory. Now the client will send its public key to the server. Now the server can calculate the common secret. Now that they both have the same common secret in memory, the server can actually encrypt all the following traffic. In my example, I'm using AES, but you can use whatever you want. So now the actual exploit code will be sent in an encrypted fashion to the victim browser. The victim browser will decrypt the exploit code in memory and run it in memory. And if the browser is really vulnerable, then the exploit code will be able to take over in the code path of the victim browser. So for example, if your shellcode is about downloading a piece of malware from the exploit server, then the browser will download this malware and execute it. And of course, you can use encryption in this stage as well, which is, again, nice if you want to bypass some protections. So this is basically what I did. But let's see this in action. In this example, I won't use any exploit code. It's just now you can see how it really looks on the wire and in the memory what I'm doing. So here is Chrome. I'm opening the exploit server. You can see JavaScript was able to run. But if you look at the document object model of the browser, you can just see some encrypted strings and some crypto parameters. But you cannot see the actual JavaScript code. Because this is just a demo application, the common secret, which you can use to decrypt this code, is still left in the memory. So if I go to the browser console, here I'm just showing that you can see the same on the wire. So if I decrypt this code in memory, because the session key is still in the memory, I am able to decipher what was the actual JavaScript running in the browser. But without the key in memory, you cannot really do that. So my very first proof of concept was created more than 3 years ago, and I chose Node.js for the implementation. Actually, it was a nice language or framework to do this, because what's really cool in Node.js that you can use the same crypto libraries on the server side and the client side. And this made the whole proof of concept process pretty fast. I think I spent like 1 day creating this proof of concept, even though I had no experience with Node.js at all. So this was my very first Node.js application I wrote. But after a while, I thought it's time to rewrite my proof of concept, so I chose Ruby to do that. Actually, it took me like 5 days to port this whole stuff into Ruby, just because of the different crypto libraries used. And now my Ruby code is compatible with all the mainstream browsers. Like it's working with Edge, IE11. It doesn't work with IE10 because elliptic curve cryptography libraries do not really work with IE10 or older. So that's it. It works for sure with Firefox, it works with Tor browser, Chrome, Opera, Mobile Safari, Mobile Chrome, Android built-in browsers. So basically, it's compatible with all the browsers you use now. And I was very, very excited of what I have created. So I created a blog post, and I tweeted about my idea. And it was very, very popular on Twitter. I got 3 likes and 3 retweets. Yes! At that time, I didn't really know what is really going on. But some months later, I realized that my idea was actually noticed by some folks. So, like 2 months later, I read a FireEye analysis where they analyzed the latest Angular exploit kit. And it was the first documented in-the-wide encrypted exploit kit. The guys were using just the plain Diffie-Hellman encryption, not the elliptic curve one. And they didn't use any zero-day in this exploit, but they did hide their shellcode with the encryption. And actually, it really makes sense in this case that they don't want to encrypt everything because all the other parts of the exploits are already known and documented, but they really want to hide the CNC, for example, where what they use to download the additional malware for their attacks. So that's why they were using encryption to protect their shellcode. So I'm not sure 100% that these guys, the Angular developers, read my blog post or not, but I think it's quite close in time that they might have been. I did had some chat with some exploit kit researchers, and they told me that, thank you, Zoli, you just made my life a lot harder, because now I am, as an analyst, I cannot decrypt these exploit codes. I cannot decrypt where the CNC is, so yeah, thank you. But it actually turned out that because these guys in the Angular exploit kit, they were using Diffie-Hellman encryption. They were using some short keys. And the guys from Kaspersky Lab, they used some clever math, and they were basically able to find the discrete logarithm used in these exploit kits, so they were able to crack it. And some months later, other exploit kits also started to implement encrypted exploit deliveries. I think the main reason these Angular exploit kit developers used Diffie-Hellman was because they were targeting older versions of Internet Explorer, so they couldn't really use elliptic curve Diffie-Hellman. So they were like, oh, I'm a sad panda. I cannot use proper crypto, so my crypto was broken. All right, so now let's just talk a little bit about the attacker model, because as I already mentioned, the title of my talk is about hiding your zero-day, and I started my research about bypassing these network intrusion detection systems. So let's see how these different things come together. So I will talk about who my attacker is, and in my case now, my attacker is the reverse engineer who tries to reverse the precious zero-day exploit. Also, my attacker is this next-generation breach detection system, and I will also talk about what these guys can do to reverse engineer my code. First of all, clearly, they can record and they can replay network traffic, as it was the case, for example, with the Safari browser zero-day in the Ahmed Mansour case. Reverse engineer can also debug the JavaScript code in the browser itself, like we did with my first demo. Reverse engineer can also debug the browser at the assembly level when we are talking about Windows. But this is not a fairly trivial task if we are talking about closed platforms like iOS. Because on iOS, if you are not working for Apple and your iOS version is pretty updated, then probably you don't have a jailbreak for that. And without the jailbreak, you cannot run assembly-level debuggers on your iOS system. So let's have a look at this encrypted exploit delivery from the network forensics point of view. Whenever you look at the wire, you will see a bunch of crypto libraries, public key exchange, and some encrypted blobs. And if you don't have the shared key, then you cannot really do much with decrypting these blobs. And you might ask, why is this different? Why is this new? Because in the past, you might have heard that exploit kits were using encryption to protect their code. But in the past, it was just some static keys. And it was because the static key was delivered to the browser in a static and plain text fashion. It just meant that the reverse engineer has just run through the deciphering with the static key, and he can do that anytime he or she wants. So it's not really a real encryption if you provide the keys to everyone. And it is also a bit different compared to SSL or TLS. And I will talk about this very soon. And I will talk about how this whole encrypted exploit delivery really affects the so-called exploit replay technique, which is mostly used by exploit kit researchers. So let's talk about SSL TLS. I'm sure you guys know that if you control your environment, if you control your browser, then doing any man-in-the-middle in the TLS layer is very easy. You just have to use any intercepting proxy, and then you install the root certificate of the intercepting proxy in your browser, and then you can easily man-in-the-middle the SSL or TLS encrypted traffic. That's fairly easy and straightforward. But when it comes to man-in-the-middling the Iron Squirrel encrypted exploit delivery, it's a bit different because SSL TLS is standardized, right? So there are standardized ways to do that. But if someone is changing the Iron Squirrel code every time, then there is no standard way you can man-in-the-middle it. So let's talk about this technique called exploit replace, which is very commonly used by exploit kit researchers. The main advantage of this Iron Squirrel encrypted exploit delivery is that the encrypted exploit traffic cannot be replayed. Once it was running in the environment and you have a network dump from that exploit, you cannot replay it, because the client will generate a different private key and a different public key, and now the client will send this different public key to the replay server, and now the common secret will be different from the first round when the client was infected, and is the second round when you try to reverse engineer the code. So in this case, the replay server either sends the encrypted data back to the client, which it cannot decrypt, or it just stops the whole exploit replay, because from this point of view, there is nothing you can do. But again, let's see this in action, how this exploit replay really works. So here you can see Fiddler. And first, I am using the plain exploit without any encryption used. And as you can see in Fiddler, it was just one plain and simple request. And it was a bit quick. What's really nice with Fiddler, that whenever it intercepted a request, you can add it to the auto-responder module of Fiddler. And from now on, not the exploit server will respond with these requests, but Fiddler. So it basically recorded the traffic, and from now on it will be replaying back. So as you might expect, because this is just a static exploit, if I use the same exploit from the browser, the exploit will succeed, as you would expect. And here you can see there are different colors used in Fiddler, that this request has been delivered by the Fiddler proxy, and it was not delivered by the original exploit server. But now, let's see what happens if I'm using the Iron Squirrel encrypted exploit delivery. So as you can see, the exploit still worked, which is nice. Now there are a bunch of different requests because of the key exchange and the crypto libraries and all of the different things. But now if I try to replay this traffic, it won't work, right? Because the client will send a totally different public key to the server, and by default, Fiddler is looking for the exact same request. And now the request was totally different because of the different public key used. So Fiddler said, I don't know what to do with this request. I have never seen some request like this, so I will just serve 404 to this client. Of course, you can try to hack Fiddler that, OK, let's just say that you should serve back the very same response to the client, no matter what public key is used. But it just won't work, because the shared secret will be totally different, right? As you can see, the exploit is not working anymore. So the researcher either has one shot catching the exploit, or he cannot properly reverse engineer it. Who is watching Archer? All right. So most of you guys, you don't deal with exploit kits and exploit replays a lot, I guess. But if you do, and this is your life, then you can see how either awesome or how terrifying this thing could be. And it's just not me stating that exploit replay is very hard when the exploit is encrypted with Diffie-Hellman or something like that. There is a blog post by Trend Micro where they are analyzing the Ostrom exploit kit, and they go into deep details why they are not able to replay the exploit traffic anymore. And there is a fun fact that it turns out everyone is using this encrypted exploit delivery for different reasons or for different purposes. As I mentioned, the Angular guys, they used it to hide their shellcode so their CNC server address is not leaked. For Ostrom, they were actually protecting the whole exploit code. And even though it was not a 0-day at the time they were using it, because the vulnerability was already known and there were patches against it. But they were basically the only team in the world who were able to create a real, proper, working exploit code to exploit that vulnerability. Which means that if they protect it with encrypted exploit delivery, the other exploit kit creators cannot reverse engineer it, so they have a competitive advantage that they can exploit all the users with this very nice exploit, while the others cannot. Okay, so in the following slides, I will talk about defense and offense. Most of the times it's just mixed on all the slides, whether I'm talking about defense and offense, but I'm really sure that you guys will be able to follow. So I will talk about how we can create some preventions against encrypted exploit delivery when it comes to the network level, and how you can detect it. I will talk about some ways to analyze it on the endpoint. And from an offensive side, I will also talk about what you can do to make blue teamers' life even harder. So from an offensive point of view, it's very, very important that you use one-time URLs, which means that you deliver your exploit only once. Because now that the exploit cannot be replayed as many times as the researchers want, if you deliver your exploit only once, that means the reverse engineer has only one chance to catch the exploit, which is hard. This is implemented in my tool. One-time URLs are very easy and straightforward if you are attacking one targeted person. But as it's the case with law enforcement, whenever they seize large websites and they want to target all the users of the website, one-time URLs just won't work for you. In that case, what I can recommend is that you keep a state of users who you already infected or tried to infect, and you only try to infect one logged-in user only once. Again, this makes analysis a lot harder. One can also put time limits between the JavaScript code to prevent manual debugging. It's fairly easy to implement it, so I did that for sure. It might make sense to remove the whole document object model after the exploit was able to run. Again, this is implemented. And I'm going to show you with the Tor browser exploit how this really works. So here I have Wireshark on port 80, and I will use Wireshark to monitor when the exploit was able to run on the endpoint, and it's leaking the IP address and machine name and MAC address of the victim browser in the clear text to a server. So here I'm visiting the encrypted exploit delivery site, which is delivering the exploit code. And here you can see all the encrypted code, but now the browser is hanging. This is very common with exploit codes. And boom, it's done. So now you can see still what was sent to the client. But because the crypto keys are already cleared from the memory, you cannot decrypt it. And you have no idea what was running inside the browser, so you cannot reverse engineer the exploit code anymore. As you can see, this variable, this session storage key B64 was storing the keys, and I already cleared it. It's not there anymore. So unless you catch the exploit in time, it's just gone. And here you can see that the exploit worked. The shellcode was able to run, and it contacted a web server and leaked some information about the client. All right. So, as you might expect, because my code is published on the internet, you can write signatures to detect the actual implementation of my Iron Squirrel framework. But I haven't spent too much time trying to bypass these signatures, but I'm sure it won't be really hard to do that. Besides signatures, surely you can try to detect encrypted traffic on the wire, but turns out there are other legitimate applications which use encryption on the JavaScript layer, so you will end up blocking those as well. And as is the case with any enterprise environment, for example, if you are trying to protect your enterprise against encrypted exploit delivery, there are some plain methods which you can use to make the attacker's life harder. For example, if you are running a web proxy, you might have the option to block uncategorized or new domains, or you can just use domain whitelisting. But again, this is a trade-off against usability, and some users might complain that they cannot access the websites they want. Actually, there is one enterprise solution which can help protecting against both encrypted exploit delivery and exploit delivery as well. And this technology is called web isolation. Web isolation works a little bit similar like a web proxy, but all the content what is sent to the client browser is basically rendered on this proxy server. And after it's rendered, it just basically screens what is sent back to the client. And this means that whenever someone tries to exploit the browsers in the enterprise environment, their exploit code will run on this web isolation proxy server. And usually these web isolation servers, they are not IE11 or whatever, so it might be a lot harder to find working exploits against that. As I mentioned, blue teamers might implement blocking uncategorized or new domains, or they can implement whitelisting. As always, these techniques can be bypassed, like one can infect any website which is already on the whitelist. This technique is called voter call. Or if you are a free letter agency, you might have the capability to do quantum insert techniques, and you can deliver your exploits that way. All right, now let's talk a little bit about how you can analyze the Iron Squirrel exploits on the endpoint. You can try to log the shared key or the client private key. You can try to fix the random generator, so whenever the code runs, it will generate the same client private keys. You can also try to do that by hooking the JavaScript code, so it will return the same client secret key every time. There is also this tool called remote debugging on iOS Safari, which might help if you are analyzing iOS browser 0 days. And you can also run something called detailed JavaScript execution trace log. And there is a very awesome project for that. And I'm going to show you that one, how that works. I'm using the same exploit as previously. And here I'm using this called Equalizer. And it's basically a debugger. And it is hooking some important JavaScript functions inside Internet Explorer. In this case, it's hooking evol and document write, which is mostly used in my Iron Squirrel framework. And now the debugger is attaching itself to the browser. And now, if I visit the encrypted exploit delivery website, the debugger just will split out basically the parameters which were used in evol or document write. And now you have access to the original exploit code, which is very, very nice. So this is one way how you might be able to catch the actual exploit code on the endpoint. Once, actually. Again, from an offensive point of view, if you want to make blue teamers' life even more harder, you can try to detect whenever the debug window is open in the browser. I didn't implement this. Again, if you are doing real offensive security, you should really do proper fingerprinting of the target before you deliver your precious zero-day exploit. But this is target-specific, so of course I didn't implement this. If you do code obfuscation a lot and you add a lot of junk code to your encrypted exploit delivery, again, that can make analysis a little bit harder. And also, as I mentioned, what you can do on your analysis environment, that you trick somehow the browser that it will generate the same private keys every time. So you can do an exploit replay. But it is very easy to detect this from the attacker's point of view. I just have to generate keys twice, and I check if they are the same. I know I'm running inside an analysis environment. So this is implemented as well. What's really fun in JavaScript is there are many, many ways how you can execute code which is similar to eval or document write. On this slide, you can see, I don't know, like 40 different ways how you can run code in JavaScript. And from a defensive point of view, that's bad, because the tool, the Evaluator tool I showed you, it can only use fixed functions. Like, I know that the attacker will use eval, so I hook on eval, and then I can log the calls of eval. But if the attacker uses any other JavaScript function call, then they will just miss the exploit code. So I'm not stating that it is impossible for a determined reverse engineer to reverse engineer an encrypted exploit delivery, but I'm fairly sure that at the end of the day, it can increase the time since someone first uses the browser 0 day until it is patched. It can delay that time with weeks or even months. A reverse engineer can surely restore the exploit code from a memory dump, but that can take a lot of time. On Windows, you can put breakpoints on typical exploit functions, like whenever someone tries to bypass dep, then they might use, for example, virtual protect. So you might try to put a breakpoint there or use some guard pages. But again, this is getting harder and harder. All right. At the beginning of my talk, I mentioned that it is possible to deliver the malware in an encrypted way now that the client browser and the server share the same secrets. And in my proof of concept code, I implemented the same. So, and it's not just that the malware cannot be seen on the wire because it is encrypted, but this malware itself I'm using is a so-called target aware malware, which means that it has some parameters built in inside, and the whole malware is encrypted basically with this parameter. And if it cannot find this parameter on the machine it is running on, it won't able to decrypt itself. And there was a very great malware written by some unknown guys called Gauss. And Gauss was using the same method. It used the path variable in Windows to encrypt its malware. And as far as I know, still no one was able to decrypt the malware payload itself because no one knows what is the correct path parameter where it will be able to run. But there is a very nice open source project called Ebola, and they are also using this target of aware malware payload. And I just integrated the encrypted exploit delivery with this malware. So now it's more safe, basically, for attackers to deliver their malware. As I mentioned in the very beginning, I implemented my code in Node.js, then I ported it to Ruby. And the main idea was that after it's written in Ruby, I can integrate into Metasploit. Unfortunately, it turned out it's a lot harder than I thought. I really tried to do that and failed. Issue is that if you are trying to write a new module for Metasploit, it's pretty easy. But this is really messing with the core of Metasploit, how it works. So it's a lot more complex task to implement it. So now what you can do is that if you have an exploit in Metasploit, you just run it against the target. You extract the static HTML file from the exploit. You put this file into the exploit folder of Iron Squirrel, and you run Iron Squirrel with that HTML file. I think one important message of my talk is that perimeter security is dying, and more stuff gets encrypted, and more mobile devices are used everywhere. So you should not depend on perimeter security as much you depended on it like 10 or 20 years ago. Since the initial publication of my proof of concept code, as I already mentioned, it was implemented by some bad guys like the Angler, Astrum, and Nuclear Exploit Kit developers. Just last week, I saw that white hat guys also started to use encrypted exploit delivery in proof of concept codes. And if you check this Chrome zero-day bug, you can see that the guys were using Diffie-Hellman encryption in that as well. I still don't know what was the main reason they were using it. Hopefully they will answer me soon. And turns out that some exploit brokers also saw my research, and they liked the idea that they can protect their precious 0 days for a longer time. As you might imagine, I did have some ethical dilemmas with this research. Like, why am I helping the bad guys? But actually, it's not that easy. And we should really ask, who are the bad guys? Like, neither offense nor defense is bad by itself. Like, whenever the FBI is using 0 days to catch pedophiles on the internet, and the only way they can do that is through Tor browser 0 days, then I'm fine with it that I'm helping them, right? And I also do believe in evolution. So if you have better defense or offense than the others, then you are the one who will survive, right? And I really agree that the current laws are not really prepared for law enforcement hacking of Tor users. That's a totally different topic. And you should really ask, what happens if you don't prepare your defenses against these kind of attacks? So, as a conclusion, Iron Squirrel could have prevented the leak of the iOS Safari 0 day, which was a lot of money lost for the guys who owned this 0 day exploit. It could have prevented the leak of the Tor browser 0 day. If someone is using one-time exploits, it can make reverse engineering a nightmare. But as you might imagine, this whole encrypted exploit delivery doesn't really deal with any endpoint exploit protections. That's a totally different topic. So you shouldn't expect anything from that. And as always, OPSEC is very important. Either you are on a defensive side or an offensive side. You should always think about that. So that's all, folks. You can download my code from GitHub. That's all I wanted to share with you. Thank you for your attention. Questions? All right, I guess there are no questions. If you do have, just find me. I will be here, and I'm happy to answer your questions. Thank you.